Okay. Hello, everybody, and welcome to this breakout session. And thanks for staying with us in room number 3. Staying with us or joining, I don't know how this exactly works, but you are now here with us, and ahead of us going to be 30 minutes fully packed with information, food for thought, and valuable insights. And talking about thoughts, if you have some thought that you want to share with us, or maybe less of a thought, more of a question, and there's a possibility to actively participate anytime via Q&A in this Slido tool. So it's integrated in Talk. On the right-hand side, there's this chat possibility. You can post any questions you have, and for us and for the person that it's going to make a presentation. And during the following 30 minutes, you are going to be guided by our speaker, Dr. Christoph Dietzel. Dr. Dietzel is the head of global products and research at DE-CIX, and he's responsible for product and project management, research, and global network design. And know what? Since we share an office and he sits every day in front of me, I'll just call him Chris. Okay, so Chris. Chris is a great colleague. He's a sharp-minded professional. He's a prolific publisher and has lots of academic papers and co-author of one or the other RFC. But Chris does not only publish and publish and lives in his ivory tower, but he also involves himself in practical IXP development issues. And accordingly, you are going to experience him today at its best. Here's already spoiling a bit. While most peering and interconnection products remain fairly stable over time, the technologies to deliver the services under the hood changing and will change significantly. Main drivers are common across different kinds of network service providers or even industries, but so are the challenges. Good, fast, cheap, pick only 2. And let me hand over now to my guest, Christoph Dietzel, and his presentation, Technology Innovation Under the Hood. Chris.
Thank you so much for the kind intro, Marcos. Much appreciated. Yeah, as Marcos teased already, I'd like to talk about technology innovation under the hood. So basically, there are a lot of changes in our ecosystem, and I'd like to highlight a bit the different angles we could look at this, where we see a lot of innovation and we have lacking a bit of innovation. And this is sort of an experiment, because usually I would, at least many of you, meet directly at our tech meeting, potentially here in Frankfurt, and come up with all these topics and ask you directly. So what I'm trying now in the next 20 minutes is just highlight certain changes, developments I'm seeing, to stipulate the discussion, the Q&A later on, which we will strictly reserve 10 minutes for. So I'm more than happy for each and every question, remark, or whatever. Let's use it. Let's use it as thought points and take it from here. So fairly well known what I'm presenting here. It's basically the ITU statistics on how many people using the internet. So it's over 4 billion people globally, and this is more than 50% of the global population, right? And we crossed the 50% mark in 2019 with 51 something. So basically what we're providing to the community is global and has significant importance. Even minor changes that we might do have a huge effect on other people. So how did actually over the past years the bandwidth increase, and specifically the specified Ethernet speeds? So if we look back at 1985, we see 10 megabits per second Ethernet. This grew into specified 1 gig, 10 gig, and lately, a few years back, or roughly a year back, 400G. So if we look at these numbers, we actually observe that this is a factor of 40,000 increasement over the past 20 years. So if you look at mobile connectivity, we basically see something similar. And what I looked at is just until 4G, right? So 5G a bit out of scope, but you can say factor 20,000, but also roughly 30,000 if you include 5G, also over the past 20 years. So But what does that mean for traffic, right? Because just more bandwidth available does not necessarily mean we are shifting more traffic, and that's what actually IXPs are known for. So if we look at a data center network, these figures date a bit back from 2008 till 2014, and we see factor 50 in traffic increase in the in-data center network of a very large CDN. However, then we look at inter-domain borders, so at the IXP, DE-CIX Frankfurt, and we see within the past 5 years, doubling of traffic. So from 5 terabit per second peak, we moved to more than 10 terabit traffic last year. So that said, what are actually the requirements in terms of bandwidth and also latency in the future? And since we saw that there is quite a significant growth over the time in Ethernet speeds and specifications of IEEE, we also see more and more requirements for latency are coming. Most of these things are still a bit further ahead, but we see that they really become reality. And if we're coming from 4K, where actually there is no strict requirement on latency, just as a reference point, if you blink with your eye, this is roughly 150 milliseconds. And the AR or car-to-car communication must be facilitated end-to-end, including processing in 100 milliseconds. If we read screens, so you look at a screen and this slide, for instance, it takes 80 milliseconds until it ends up in your brain. And the VR is just a quarter of it, because our eye is very, very sensitive to the movement to our right in the horizontal movement and vertical movement. And if the content is fetched as we go, this is a bad user experience. So we see according to this statistic or this overview derived from some Nokia work, we see the killer applications is VR, AR in terms of bandwidth and latency. So next, we actually ask ourselves, so how does the latency improve? How did it improve lately, and what shall we expect in the near future? So if we look at the most important part, the propagation delay, we basically saw an increase. This is obviously because we also have way flattening of the internet topology, meaning that we actually have way more peerings between the networks compared to 10 or 15 years, maybe even 20 years ago. And this means the physical distance is getting shorter, and this means the propagation delay actually really improved over the past years. So, but still, way to go. And lately, with the introduction of 5G technologies and all the, you can also call it a bit buzzword world, where you have heavy edge deployments, we expect the propagation delay even increasing, not because the propagation is faster, but because physical distance getting shorter. So transmission delay is actually the pushing of the bits onto the link. That basically did not change, right? We can do more in parallel. That means our bandwidth is higher, but the delay didn't improve. The same for processing delay of packets coming in, header processing, that actually didn't change, or at least not significantly. What actually happened over the past decade is a change in queuing delay. So basically, due to deep buffers, buffer uploads, actually queuing delays increased. So with a negative impact on performance. So asking the question, why don't we actually still not operate the internet at speed of light? And here is a very nice outcome of a study where actually the authors looked at 50 metropolitan areas across the world and looked at the road distance. So they took just streets and figured out in a huge matrix, how far is it from one city to the other. And then this is only the reference, it's the green bar. And then you look at the fibers. And on the x-axis, you actually see the inflation over the geodistance, meaning the factor how much longer you need to go. And we see that for 60% of the fiber routes between the cities, you actually have an inflation of factor 2, meaning twice as much geographical distance has to be covered. And you see that the long tail, so for the remaining 40%, is even factor 3, 4, and the long tail is obviously fairly long. So one significant reason why we don't operate the internet at speed of light is our fiber equipment, the fibers in the ground are not built out as they would need to be. So what other options do we actually have? So we could also have internet in space or via space. I mean, now it's since SpaceX is doing this, it's actually everywhere, even in mainstream media. But the exciting part is two things in our view. And that's also where DE-CIX is working together with ESA to come up with a solution for how to integrate such an internet in space with a stationary internet. How many ground stations do we need? Where do they need to position? And the other part is how can we actually route in space, given that actually our routers are moving towards each other, and the signal run times might change significantly over time. But all these innovations and things that are ahead of us, but one thing we basically lacking a bit. So if we talk about topological innovation. So to me, and just to frame those two terms, there's a public internet and private networks. And you'll get in a second to what I mean. So the public internet is what we use. It's BGP, the routers, the ASs, all more or less IP-based, whether V4 or V6. And there's these private networks. In many cases, they use the very same technologies. However, the bigger ones, and specifically the CDNs and clouds, actually develop their own protocols, technologies, or even gear. So here is something I've stolen from the Google website, where they describe their network. And you see actually here in the core, there are their data centers. Around this, there are their edge points of presence. So there are POPs in the carrier hotels. And then there are the edge nodes, which are basically off-net or on-net, depending on the direction, caches. And this really shows that on the on-net caches, I mean, they're running their own servers in a different network. However, what they do in the blue one, which is the internal network, is quite different from what works on the public internet. So to just give you a few examples, this might either be things like the data center networks with custom protocols they're really using, and also custom routing switching gear. So they talk to the vendors. They have either white box solutions or they have really customized chips, and they're also working on the chipsets. They have middle boxes deployed in their networks, which can act as WAN optimizers. So the B2, B4 backbone routing links using SDN to really utilize up to 99% of the links without packet loss, proxies, firewall capabilities, and within their networks, quality of service that really works, and also security features. And if we talk about the public internet, we all know that at least if it comes to interdomain, this does not really work well so far. So why should we care so much, right? Let them do what they want, and the internet, if needed, will adapt. And one great feature of the internet is it is stable. And also the standards are very stable. So why should we care so much here? Well, private network adaptations are just not compliant with the architecture. That means basically I might implement my routing different than you do. And actually, there is no control measure to harmonize both. An example is huge CDNs don't really do their best path selection based on the AS hops, but rather on an overlay network which actually measures the latency. That might be a good thing for one network. And if another big one adapts as well, that also works. However, at some point, if everyone does it and it does it differently and it's not compatible to each other, we're actually running in some arm races or some side effects. And when part of the architecture it is really reusable. So everyone can expect certain firewalling capabilities, certain on-net services, and just by having it standardized, other technologies and interconnection can even build on top of it. So it should be, and we should push harder for consistent with internet design guidelines. So universality, extensibility, and generality. So then again, we have technological innovation and really technologies that change significantly. So here is a quick trend overview and also the remark how this relates to DE-CIX and what we're doing here. So for instance, network function virtualization, right? We're thinking of products and services such as router as a service. So you have specialized networking, hardware replaced by software on general purpose servers. That really allows short innovation cycles since you just need to adapt the software. You remain more flexible and you can run quite dynamic tasks and workloads. On the other hand, there's a software-defined network NP4. So you could implement, as in my example before, and some of the CDNs did, prefix latency-driven routing. So this is not really following best path selection, but rather you measure latency to prefixes, and then you actually route accordingly. I mean, I know the complication of measuring latency to a prefix, which technically does not really work, but at least at a fine-grained level or with some abstraction, you will be better off than using just AS path length. Another thing is edge cloud and mini data center for special purposes, right? So essentially what you're doing, you extend the idea of on-net caches and bringing workloads even closer to the user and exploiting the advantages of network function virtualization or SDN. One network function could be you could terminate really transport end-to-end connectivity for a user just on the on-net cache and not somewhere in your backbone network. Even though you still might, in some cases, transport the traffic from elsewhere. So this improves latency, but also has some integrated security aspects to it. So quickly about the SDN, because nowadays I see it's all over the place, but basically it is used as term only to describe that there is more flexibility in how we initiate or instantiate or configure our gear, so our routers and switches. However, the concept per se of splitting control and data plane, and by this allowing more flexibility, is quite some years old already. So here, this is not necessarily a slide where you need to understand everything, but see that it actually goes really back with 1995, or maybe even some concepts are even older, where people proposed a separation of control and data plane and a more active control loop with the routers. So the same we're actually also doing at ISPS, at DE-CIX, right? So we have a layer 3 control plane that is separated from our data plane, our route servers. And now for the future, the thoughts are, okay, but what do you need as customers? What kind of routing would you like us? What kind of measurements? Or do you want to do it yourself and just want to have a better programmable interface to the control plane? Or are you fully satisfied with BGP for years to come? And if we look at this from a concept picture, right? So we still have our hardware, but this could also be programmable fabric. 2 more words on this on the next slide. And then we have the interface to our own systems, where we integrate the route server, monitoring platform, and everything else that we need. But we can also allow applications running on top that are customized by customer and could be different for each customer, differently instantiated. However, the huge challenge here is to really have a middleware software stack that has all southbound interfaces, all northbound interfaces, and all the required functionality. The programmable data planes are coming up since 2-3 years. They're around, and actually I find them super useful and interesting for certain use cases. Of course, the prime use case that I've seen is DDoS mitigation. So what you can actually do, you can write code really on the hardware. It's not FPGA, but sort of layer abstraction layer above it, at least as a user perspective. And the packet comes in on the left side, you pass the header, and you can perform certain match and actions. in the ingress pipeline. That means also modifying packets and then pushing it down the pipeline. You can also do again changes, and then you can simply output it. And that could be really matched with very simple rules to reduce amplification DDoS attack or mitigate certain protocols in the first place at line rate. So what do we see, and will we see in the internet in the future? A revolution? No. Fortunately or unfortunately, it's rather an evolution, and it brought us here. However, the more we now want to have better latency and higher bandwidth, we actually need to continue innovate. And it's great that the CDNs innovate in their networks, but it would be even better if it's open and extensible and everyone could participate in this. So basically, where we locate our ISPs and our POPs becoming less and less relevant, at least if the big contents are pushing that traffic because of on-net caches and other technologies. The network's becoming more and more dynamic because we can program them, so we can interact with them and don't need to configure them and leave them as they are. There's are more abstraction layers and even more to come. So we have multiple more virtual networks, which is also closed user groups or some separation of the public internet, so the private networks. Of course, the bandwidth will continue to grow and we will transmit higher volumes. And the latency due to shorter paths are actually even to be shorter in the future as well. So that's the brief overview from my side, and now I'm more than happy to have your questions.
Okay, thank you very much, Chris. I really love if I get some questions from the audience. Networks are bidirectional. You know, it's not just us talking and talking, but there is a channel back. And while I'm waiting for the questions to come, I have a question, because you started talking about VR and AR and the ESAT and satellites, and then I started getting dizzy. And now, down to earth, pun intended, no? Satellites down to earth. What are real technologies from the ones you have presented that might be pursued by DE-CIX to be turned into real products?
So what we really think about is the SDN and P4 part, but with very specific use case, obviously not as part of the peering platform, but also network function virtualization, right? So even if you think about the cloud router teased by Thomas earlier today, even if you think router as a service for networks or for, I'd rather say, participants who don't run their own network, but rather want to consume very good performance and huge bandwidth as a service.
Okay, I see. Looking at the questions, one thing that left me thinking about this when you started talking about the innovation in the private network area. Okay, so you start talking about data centers with proprietary protocols and tailor hardware to do some stuff, and yeah, that left me worrying, because I started thinking about the public internet. What's going on the public internet, and how does the power of innovation of the public internet look like? And more concretely, can you think of any concrete approaches to maybe improve this power of innovation?
So this is a really hard question, and but I like on the same time that you're really pointing this out, because that's exactly the challenge that we have, right? So we go to IETF, and standardization takes, I don't know, from 5 to 15 years, maybe if you're really fast, 3 years, but guess even for smaller extensions, changes, we're not any faster. So what do the big guys do? Well, they are in possession of both ends and their own internal network, which is very, very close to the end user. So they just do it, they just deploy it. And of course, it totally makes sense for them and also for us as end users. But we need to find some more means to get them engaged in standardization or in public extension efforts, right?
Exactly.
And so my view is we are quite good in packet pushing. I mean, there are limitations, but let's say until the IP layer, everything sort of works fairly well. But all the stuff that is on top, and you see a lot of in-network smartness, so smart NICs or a lot of middle boxes, which do a whole lot of things, right? But they are by no means standardized in any way. Some might argue they don't need to, but I think if we could make this happen, this would also be great opportunity to even more value services on top and also the smaller networks to participate in these efforts.
That makes perfectly sense.